Okay, so today's lecture will be actually short, so we will go to a couple of problems. So problem 744, which is an industrial plant operates under the following conditions. The load is 120 kilowatts. The line voltage 480, angle 0 volts, RMS, 60 hertz. The power factor is 0.84, that's the power factor of the load. And the line impedance is 0.1 plus j.2 ohms. Determine the power factor at the source. So basically, this question says that we already have a load, and we know the load properties, which is 120 kilowatts, 0.84 lagging power factor, and we know the voltage at the load, which is 480, angle 0 volts. And this voltage, it says the line voltage. Is there any information about this? Actually, since it's line voltages, which is basically in RMS, it's already been in phasor. Then we have the line impedance 0.1 plus j.2. What do you mean by line impedance? Basically, most likely when we have a source, we have power lines, then it will go to the load. The power lines have their equivalent impedance. Or sometimes like in DC we used to call it resistance, now in AC we'll call it impedance. This is impedance of the power lines. Here we found its dominant, which is 0.1 plus j.2. That's the equivalent impedance of the power lines. Basically the power lines, there is a resistance and inductance. So that's what we see in real life problems. Now let's start analyzing that question. So problem, again, we are in 7.44. Again, we have a load based on that question. The load given as here plus minus V load, which is the voltage 480 volts, angle 0 degrees volts. Again, this is RMS representation. Then the load also, we have some information about it, which is the real power of the load, 120 kilowatts. So when you go to, again, when we go to the question, see it's 120 watts, 120 kilowatts. How can I recognize, is this value real power? Is this value reactive or apparent power or complex power? Look at this, it's only a value or a number, then definitely it's not complex power. Okay, now I have three scenarios. Is it real, reactive, apparent? Look at the units. The unit is in watts. Watts means real power, right? If you see the units volt ampere, then it's going to be what? Apparent power, right? S. If the unit is var, it's going to be what? Reactive power. Okay? So it's very important. It's just sometimes like playing with the words. Here it's kilowatts. Maybe some other questions can be var. Some other questions volt ampere. Then here we have the real power, 120 kilowatts. Having one quantity, since it's complex power, we need to have two quantities. Something related to the magnitude, something related to the angle, or something related to the real part, something related to the imaginary part, or a mix of them. So we have only one information, which is 120 kilowatts. We have another information, which is the power factor of the load, 0.84. 0.84, and it is lagging. Now, when I have these two information, I can find the complex power. Okay? Let's finish like the question, then we will see how we can find the complex power. Then the other thing, we have the line impedance, which is here, Z line, 0.1 plus j.2. Then we have a source. We don't know the source voltage. We don't know the source power factor of the source. Then the thing which is we need to find the source voltage and the source power factor. How can we find this? Again, we have the load voltage. Then if we know the power, can we find the currents? Yes? So basically we need to plan our answer as we can imagine the current going out from the source. So here is, I'm going to call it as I source bar. And this problem is already in phasor. I don't need to convert anything from phasor to time and etc. So this is I source. Okay. I source is unknown. If we figure out a way to find I source, then we can find V source easy by applying KVL. How? Let's try, I'm going to label the voltages here, plus minus V line, and this is plus minus V source. So I'm going to do KVL, this loop, loop I. Start from the left bottom corner, then travel clockwise. It's going to be negative V source plus V line, and don't forget the bars because they are, all of them are complex quantities, plus V load bar equal to 0. Now, V source is unknown. V line is actually I times Z, which is Ohm's law. I source times Z line. Plus V load is known. We already know V load. Okay. So based on this, we can calculate V source as it will be I source times Z line bar plus V load bar. Now we know the values. Let's substitute the values that we know. I source is unknown, but Z line is given as 0.1 plus J0.2 plus V load, which is 480 angle 0 degrees. Then by look at this equation, the only unknown thing, which is I source, right? We don't know I source. So our target, if we figure out a way to calculate I source, we can find V source easy using this formula, right? Now, the challenge is how to find I source. Again, let's recall our procedure in solving the circuit analysis. Go to the extra given information. What's the extra given information that we have? Look at the circuits. The power of the load, right? So we have real power of the load. We have power factor of the loads. So now one of the challenges that you need to figure out, if you know it's now, then it will be easier for the rest of this course, because we are going to use this in the three-phase analysis. We're going to use this in the transformer, in the three-phase motor. So we're going to use this a lot, which is basically you already have some information about the power, but you need to calculate the complex power based on this. How can I calculate the complex power? It's actually complex numbers analysis. How? We know PL as power, real power. Power factor is the cosine of the angle, right? Now, here is the trick, which is we need to know how to find the complex power. Now, we have several scenarios. Let's assume scenario 1, that's the power given as a volt ampere and power factor. That's one scenario, which is basically you already know S, and you can say theta equal to plus or minus cosine inverse of power factor. Plus if it is lag, minus if it is leading. Then, how can we calculate the complex power? Basically, we will say S bar equal to S angle plus or minus cosine inverse of power factor. That's case number 1, if we know the power given as volt ampere and power factor. Case number 2, the power can be given as real and reactive power. How to calculate the complex power? Basically, S bar will be P plus JQ, right? Then you can convert it to polar, rectangular, whatever you can do. That's how we calculate it. Step number 3, you might have the power, real power, and power factor, like what we have in this example. This case, how can we calculate the complex power? You will say that the complex power will be P over S over power factor. P over power factor, angle plus minus cosine inverse of power factor. Step number 4, case number 4, when you have reactive power and power factor, how to calculate the complex power? It will be Q over square root of 1 minus power factor square angle plus or minus cosine inverse of power factor. So you need to master all of these 4 scenarios. If you understand them, that's fine. Then everything will be great. You don't need to memorize them. You can write them in your note sheets. Okay? Now with these 4 scenarios, which one should I use? Look at the units of given that in the extra given information. Look at the units. So the units, is it watts, power factor, is it var, power factor, is it volt ampere? So when you look at this example, let's go with our example here. We know real power and we know the power factor. So basically we can use number 3 here. So we can say S bar will be P over power factor plus minus cosine inverse of power factor. Then we have 120 kilowatts times 10 power 3, power factor 0.84, angle plus or minus, it is lagging power factor, therefore it's going to be positive because it's lagging. So plus cosine inverse of power factor. Again, it's positive because it's lagging. If it is leading, then it will be negative. So the answer after making this analysis will be 142.9 times 10 power 3, angle 32.86 degrees. Remember, when we calculate the complex power, it's highly recommended to convert this to rectangular coordinates. That's when you box your final answer. Now, I'm not boxing my final answer, so that's fine. I can keep this in polar coordinates. That's fine. Because again, the question is not to calculate the power. Now, what should I do? Again, use the extra given information to calculate the unknown thing. What's our unknown? Now we know the complex power. What's our unknown is the currents, right? Let's go to the loads. Here, the loads. We know V loads. We know S load, right? What's the unknown? Is I. How can we calculate I? Do you know the complex power formula, which is V equal I times, S equal V times I conjugates? That's it. We know S, we know V, then let's calculate I. So according to, according to the complex power, S load equal V load times I load conjugates. Now we need to calculate I load. So I load will be S load over V load, all of it conjugates. So it's going to be S load 142.9 times 10 power 3, angle 32.86 degrees, divided by V load 480, angle 0. And again, don't forget the conjugates. This is one of the common mistakes when we calculate the complex powers, missing the conjugate. So what I'm going to do, don't put this in the calculator yet. Do the conjugate first. So when you do this in the calculator, stop, don't do it now. Let's do the conjugate. The conjugate means the angle will be negative. So it will be angle negative 32.86 degrees. The conjugate for 48 angle 0 will remain as is because the 0 is negative, it's neutral, so there is no negative 0. 480 angle 0. Now, how we can calculate this? Since it's in polar, and sometimes the calculator, maybe we can get in troubles in the polar, so you can say, let's divide the magnitudes alone and subtract the angles. So the angles, since the negative 32 and 0, it will be negative 32. Then the only thing what you need to do in the calculator, which is 142.9 times 10 power 3 over 480, angle negative 38.86 degrees. So just put this expression in the calculator. Don't put the angle because again the angle will remain as is. So which will be, after put this, it will be 297.619, angle negative 32.86 degrees. Now this is I load. Okay? Now since I calculated I load, I'm not done yet because I need to calculate V, the voltage source. So I'm going to use this results and substitute it here in the KVL that I did. Okay? Let me give you a few seconds to write this expression, then we're going to move to substitute IS. Okay. Now, let's substitute this here. Then V source will be I source, which is 297.619, angle negative 32.86 degrees, times 0.1 plus 0.2 plus 480, I'm sorry, 0 degrees, angle 0. Then, when you put this in the calculator, make sure this shouldn't take more than 30 seconds to insert and get the answer. And sometimes when you put in the calculator 480 angle 0, it will give you an error. Some calculators like this. Why? Basically, 480 angle 0 is the same as 480 without angle. Some calculators, not every calculator, some of them it will tell you if you put angle 0, it will give you an error. So anyway, when you enter anything with angle 0, you don't need to enter the angle. Just enter the number as is. Any number with angle 0, enter the number as is. Don't worry about inserting the angle with 0. Okay? Then after substituting this in the calculator, again, it shouldn't take more than 30 seconds. It will be 538.362 angle 3.605 degrees volts. This is the voltage source. And remember, our target is not only to calculate the voltage, it's to calculate the power factor of the source. How to calculate the power factor of the source? The best approach is, let's calculate the complex power first. Then from the complex power, we can do whatever we need. We can do the real part, imaginary part, converting this rectangular to polar, etc. So how to find the complex power of the source? It will be V source times I source conjugates. V source, 538.362, angle 3.605 degrees, times I source, which is, we calculated it as 297.619, angle negative 32.86 degrees. And don't forget the conjugate again. So before substituting this in the calculator, do the conjugate first in your sheet here. So let's do the conjugate first. So 538.362 angle 3.605. It will remain as is because the conjugate only in the current, not on the voltage. So it will be 297.619 angle. The conjugate of the angle will be positive, and negative will be positive, so it will be 32.86 degrees. Now you are ready to substitute this in the calculator, or you can say, let's multiply the magnitudes together and sum the angles together. So either way that you prefer. If you have difficulties in writing the polar in the calculator, you can do the multiplication of the magnitudes and adding the angles. So the overall answer will be 16.02 times 10 power 3, angle positive 36.465, and the unit is degrees here. The unit is volt ampere. Our target is not to calculate the complex power, so you don't need to convert this to rectangular coordinates. If the question says find the complex power, then when you box your answer, you must convert this to rectangular coordinates. But now, our target is to calculate the complex power. The power factor. How to calculate the power factor? Power factor of the source is actually cosine of the angle, right? And it can be leading or lagging, depending on if it is negative, leading, if it is positive, lagging. Now, look at the angle. Is it positive or negative? Positive, right? So therefore, power factor of the source will be cosine of 36.465, and it is lagging. Then you can substitute it, which is going to be 0.744 or 774, and lagging power factor. Then problem done. You can box this final answer. So you see, like this example is cumulative. We are using all of the AC circuit techniques. We are using complex powers. We are using the different format. We are using Ohm's law or KVL, KCL. Any questions? Okay. So this is a very practical example. This example is used a lot in our real life applications when we deal with some industrial loads to make sure that how much power do we need to supply, or what's the source voltage will be, or how this will impact on our utility grid. Now I'm going to go to another example. Let's wait a little bit so we can write. Yes.
Explain power factor of load versus power factor of source.
Okay, that's a good question. So here in this analysis, we have the power factor of the load given. The power factor of the source is different. What's the point? We have source and load. They should have the same, right? They should be the same. Source and load should be the same. That can be correct if there is no line impedance. So the thing here, we have a line impedance. This will impact on the power factor. While if the circuits, source and load without a line impedance, then you don't need to answer anything. The power factor of the source, the same as the power factor of the load. But here what matters is we have a line impedance that plays an important role. So you can see that the power factor of the load is 84%. The power factor of the source, 77. This means there are, now it's from 84%, now 77, there's a poor source power factor. Why? The reason, because we have a losses, kind of losses going on. These losses going on were because of the line impedance. And it's very important for these four that I wrote here, these four formula and how to find the complex powers. Those are very important. We will use this in the course for the rest of the course, I think, until the last lecture. Okay? Any other questions? Now let's go to another problem. So the problem 744 is an example of power factor analysis with complex power. While I'm going to go to another problem, 751. This 751 is considered as power factor correction problem. So this is another type of problem, of real life problems that we see. So 751, an industrial plant operates under the following conditions. The load is 110 kilowatts. 110 kilowatts means what? Real, apparent, reactive, complex power. What does this mean? Real power, because in watts. And we have the line voltage for 480 volts, 60 hertz. The power factor is 0.76, lagging power factor. Now determine the value of the capacitance, which when placed in parallel with the load will raise the power factor up to 0.9. So this is, again, one of the common problems that we see nowadays and when we deal with industrial loads. So the vast majority of our industrial loads are based on induction motors. These induction motors are actually equivalent circuit of it based on inductors. These inductors are consuming a lot of reactive powers. These inductors' behavior will cause a lagging power factor. Lagging power factor here is we have 76%. 76% as a lagging power factor will be poor. This will impact our utility generation, the power utility generation. Therefore, the power utility, they are monitoring the power factor at the load or at that industrial load. They found that it's 76%. It's poor. Then they sent a notice to the industrial load and telling them you need to fix your power factor. You need to impact your to enhance the power factor. If not, you need to pay a penalty, this amount of money per hour. It can be, for example, $1,000 per hour. It can be $500 per hour, depending on the agreements. If you cannot improve your power factor, you will get this penalty. So the electrical utility will have a power factor meter in the industrial loads. They will monitor the power factor. Again, they will monitor if it is poor, then there will be a penalty. You need to pay extra. So the industry, they didn't like this. We don't want to pay like $1,000 per hour for that. We need to avoid this penalty. They go for you as an engineer. You are an engineer. You are a problem solver. We have this problem. Okay, so your boss tell you, you have your job. Get this done, or you will be fired. So what are we going to do? Let's go back to the course, 3810. Okay, in that course we say, okay, there's a power factor, and the power factor correction, basically we need to install a parallel capacitor. And that parallel capacitor will work to enhance the power factor. Okay? So you will go to your boss. You will say, okay, we need to purchase a capacitor or power factor correction, which is by purchasing capacitor bank, and we will install it there. Okay, so we'll tell you, okay, take the lead. Come on, give me which device that we need to buy. So you will go to the market. You will see several parts of the capacitors. You can find something large, something low, or depending on the cost. So the next topic or the next thing, now we agree that we need to install a shunt capacitor or power capacitor bank or whatever we call it, capacitor. So your target as an engineer is not only to say, let's use this. What's the value? What's the best value that we need to use so we can improve the power factor to be 90%? We can avoid the penalty. What should I do? We need to do the analysis, power factor correction analysis, so we can determine the value of the capacitor. Then, for instance, if, for example, we say we need to have a value or the capacitor value is around, for example, like 3 or microfarad or 3 millifarad, whatever. Then you will go to your boss, say, okay, let's buy this one. Okay, you will buy this one, install it, solving the problem, save your job, and save money for the company. Now, how can I know? Is it 3, 1 millifarad, or other values? Basically, let's do the calculation. Okay. Now, for me as an engineer, since we are problem solvers, we have a load here given information as 110 kilowatts times 10 power 3 watts. If this is real power. And we know the power factor given as 0.76. This is, I'm going to call it power factor original. The power factor new that we need to improve it to be 0.9, and all of them are lagging power factor. Then also we know the frequency is 60 hertz. We know the voltage of the load as 480 angle 0. This is V load bar. And the power, this is called PO. This is the power factor of the power original, the real power of the original load. Then what do we need to do? How can we do the power factor correction? You can follow the procedure in note sheet and worksheet 11. Worksheet number 11, power factor correction. So basically following the procedure, and we already mentioned in the previous lecture, so let's do with the original situation. With the original situation where there is no capacitor, Q original equal to P original tan of theta original. We don't know theta original, but theta is cosine inverse of the power factor. So it will be P original tan of cosine inverse of power factor original. And it's going to be plus or minus depending, is it leading or lagging. Let's substitute the values. P original is 110 times 10 power 3. Tan of, since it's lagging, then it's going to be positive. Cosine inverse of power factor original, which is 0.76. Then you can do first like the cosine inverse. So it's going to be 110 times 10 power 3. Tan, if cosine inverse, it will be 40.536 degrees. Then the answer will be 94.07 times 10 power 3, or in other words, 94.07 kilo. And the unit is var. Since it is reactive power, again, the unit of the reactive power is var. Now I'm done with the original case. Let's go to the next case, which is when we add the capacitor. So the capacitor bank will be added in parallel to improve the power factor. So how we do this? Basically, we'll say step number 2 with the new case when we add the capacitor. So Q new is very similar to the original, but we will say Qn equal PO times theta n, tan of theta n. So basically we will use the theta, the new power factor. So it will be PO tan of plus minus cosine inverse of power factor nu. Then substitute the values 110 times 10 power 3 tan of positive plus cosine inverse of power factor nu is 0.9. And it is lagging, that's why I make it positive. Then it will be as 110 times 10 power 3 tan of 25.842 degrees. Then the answer will be 63.09 times 10 power 3, or in kilo, 63.09 kilovolt, such that again, kilo is 10 power 3. Then now I'm not done yet, so let's do more steps. So step number 3, we need to calculate the equivalent capacitance, or the reactive power supplied by the capacitor, which is going to be the absolute value of delta Q, which is going to be the absolute value of Q new minus Q original. Then it's going to be as 63.09 minus 90, what was the other value? Yeah, 94.07, all of them in kilovar. So it will be as 30.98 kilovar. Now we determine the value that the capacitor need to generate. We still need to calculate the last step, which is the capacitance, the value of the capacitor. So you'll say C equal Q sub C, which is the Q of the capacitance, over V square times omega. V square, keep in mind, use only the magnitude, don't use the angle. Anyway, the angle here is 0, but I mean, keep in mind, you need to use the magnitude. So it will be 30.98 times 10 power 3, because it's kilovar, divided by 480 square, times omega, which is 2 pi times f, 2 pi times 60. F is given as 60. Then the answer will be 356.654 times 10 power negative 6 farad. We didn't refer to it as times 10 negative 6. We will write it as a micro. So it will be 356.654 microfarad mu f is microfarad. Then this is the value of the capacitance. Then you will go to your boss, say, let's use this value. Then this will save you. Any question? Yeah, 480 squared, because V squared. This is the V squared.